Good morning, everyone. Today we are going to be introducing deep learning into the course. So everything we've done so far has prepared us for this moment, and it's one of my favorite sessions. So let's get started.
Yep. So let me share my screen. So I have this whiteboard prepared in advance. It was from a previous session. If something seems confusing, just let me know. I can redraw these things from the beginning, but I think it would take much time to redraw these things. So I think it would be better if we um, talk about whatever's already drawn there. Okay, so um, whatever we have been doing so far, the majority of the concepts stay the same. It's just that the model that we've been using for the linear regression and the logistic regression, we just have to now replace that with something that is more complex, which is able to capture more complex relations between inputs and outputs. So you saw in the linear regression that what we were trying to do was to capture the relation between input and output using a straight line. In logistic regression, we took the same concept, just applied this nonlinearity on it in order to squash the output between a 0 and a 1 to convert it into probabilities between 0 and 1 so that we can then just throw a threshold and classify the output. Um, a neural network is just a bunch of logistic units combined together in order to make it more um, you can say diverse, which is then able to um, learn the mapping between input and output. So the question that comes to mind is why are we seeing this sudden advancements in neural networks? Why are they so going so crazy these days? And because they existed since 70s and 80s, what went what caused this sudden boom? And the sudden rise in the popularity of deep learning and their power comes from two things. First thing is um, the compute power that has kept on increasing since 2000. And the second thing is the availability of the data. So previously, although the basic building block of a neural network was there, but when people started to make these architecture bigger and bigger, it became much harder to train them using the available compute power and the amount of data that was required. But as both of those things started rising, the popularity and the performance of deep learning also started to shine. That's just a general comment about uh, why this sudden boom in deep learning. But let's begin. What is a neural network? The basic idea is inspired from a biological neural network, of course. But although the idea was inspired from it, people in the neuroscience still say they don't understand how biological neural networks work. So you cannot say that this is something that is exactly what is going in the brain, but the idea is loosely inspired from the brain. So what you see here is what is called neuron, biological neuron. So in biology books, you'd see a diagram that looks like this. So uh, for a second, just think about this um, picture here. So we have what is called these dendrites, and then there's this long tube, and then this part of it is called axon. You see the cursor?
Yeah.
Yeah.
Okay, these are called axons. This is called dendrites. This can be considered a typical input, and this can be considered an output. And then this is the nucleus of the neuron. So what happens is these dendrites receive inputs. They then perform some processing on it in the nucleus, and then they transmit the processed signal using electrical impulses to these axons, which is an output, which are then connected to the dendrites of a second neuron. So usually it is said that there are around 100 billion neurons in a human brain, and there are around, I think, 1 or 2, or I'm forgetting the exact number, about 2 or 3 trillion synapses, um, meaning 3 trillion connections that are that this neuron is connected to in its close proximity. So there are those many connections. So the idea, just like I discussed, some inputs is coming, some processing is happening, and then it is producing an output, and then that output is taken as an input by another neuron, and that's all that at least we know about what is going on. And then the way neurologists study when they are looking at some phenomena is all they do is suppose they are interested in particular location of a brain, what's happening there. All they measure is these electrical impulses, and based on that, they deduce that because when that phenomena happened, lots of neurons were firing here, so maybe this region is responsible for this phenomena and so on. But not much is known. Now, how do we take this idea from the um, this biological neuron? How do we implement this in a computer? So I have lots of things written down here. Maybe the order that I'm going through these is not perfectly, it's not very good, but whenever you feel lost, just ask me a question and then I'll try to fill in the gaps. But what I'm trying to talk about here now is how do we, this is a biological neuron. What is its artificial equivalent in a computer? So in a computer, what we do is we take some input. This input can be considered as the features that we were seeing in the previous sessions. We feed those features. They're connected to these, you can call cells or artificial neurons. The way they are connected to those artificial neurons is where these connections. So suppose this is a neuron, so this is one cell. How is this input connected to it? These inputs are connected through what are called the weights of the model. So suppose this is x1, this is x2, dot 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 xn. How do this neuron computes its output? Well, all of these inputs are connected to this neuron using a set of weights w1, w2, dot 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 wn. The way the output of this neuron is computed is exactly similar to what a logistic regression was doing. So we take the input. If I try to write it here, we take this input x1, multiply it with the respective weight w1, add to it x2, multiplied with w2, plus dot 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 xn, which is the nth feature, multiplied with wn, which is the nth weight associated with that. We just simply multiply them together, add all of them together, and then we apply this nonlinearity or the activation function on it. So the activation function, just like I said, it's a logistic unit, and you remember in the logistic unit, the nonlinearity that we applied was called sigmoid. So what the sigmoid function was doing, it was just simply taking this and plugging it inside this equation, which is 1 divided by 1 plus e to the negative, let's call this z. And that's how the output of a single neuron is computed. Do you have any confusions here?
Can you draw that one just so I can remember what it looks like?
I think I might have it here somewhere. Yeah, here. Okay, here's the generic form.
Oh yeah.
Or the,
I meant, could you just draw on the x-y axis what a sigmoid function looks like, just so?
oh yeah,
just to
of
find
course.
that. Yeah.
So the sigmoid function, it looks something like this. So this x-axis can be considered as the z. This is the negative side. It's the positive side. The larger the negative value is, this sigmoid tries to make this output as close as possible to 0. This is 0, so it asymptotes at 0. And on the positive side, the longer this, the greater the value of this z is, this sigmoid tries to asymptote it is 1. So it's doing nothing but just simply squashing the output between a 0 and a 1. Okay, if we see this diagram here, this is a more maybe cleaner way of representing how artificial neuron, which is also called a perceptron, is producing its output. So these are the three features, x1, x2, x3. We just simply associate these weights with it, w1, w2, and w3. The way this output is computed is these respective weights are multiplied with the respective features, and then we sum them all together, add a Bayes unit on them, and then apply the activation function on it, and that's how it is producing an output. This is the output. Does this make sense?
So it's a linear combination of all of the inputs plus one
Mhm.
bias.
Plus a Bayes, and then on top of that, a nonlinearity.
On top of that, the nonlinearity. Which part of this equation is the nonlinearity? The A?
Yeah, so this A is just simply representing that we apply a nonlinear linear function in it. If you look at this equation here, this is, I mean, that's how you should usually write it in mathematical form. So the linear combination plus a Bayes unit, and then on top of that, this nonlinearity. So usually the nonlinearity, like for beginning neural networks, sigmoid was used as the nonlinearity. But as you'll see with time, lots of different activation functions or lots of different nonlinearities were tried, and then it was shown that there are other nonlinear functions that can perform better. This is just the mathematical overview of it. I think I misordered this. I should have first talked about this intuition behind why neural networks work. But just like I said, I've just written these things and I have completely forgotten the order of it. But let's just try to talk about the significance of a neural network using this hypothetical example. Suppose we have these features associated with an item that we want to predict a probability for if it's going to be a top seller or not. You can consider it as a T-shirt or something. So what could be the features of such an item? The features could include the price of the item, the shipping cost, the marketing that has been done for it, and the material it is made up of. So these are the features that we have, and the goal here is to predict if if this is going to be a top seller or not. Is this example clear to you?
Yeah.
Okay, so how can we do this? Suppose we want to um, we can employ a logistic unit in order to do this thing. How can a logistic unit perform this task? Well, it can just simply take these features as inputs: price, shipping cost, marketing, and material, and then apply the respective weights on them, and then compute the output using this sigmoid activation function. And it can compute the probability for it, which is the probability if this is going to be a top seller or not. But if you ask someone that is expert in in this area, he or she'd tell you that although these are the features that you are using, but there are some higher order concepts or some more refined abstract concepts which would make it more easier for someone to predict if it is going to be a top seller or not. One of the factors, high order factors, could be the affordability of this shirt. So is it affordable enough? Another aspect could be, are people aware of this item that you have? Another thing that could be valuable is the perceived quality. So what do people think about this item? That is it of a high quality or low quality? Now, if you look at these factors, these are not directly visible or not directly available to us from the raw features. These raw features combine in certain ways, which make these factors. So suppose how can we determine the affordability of this shirt? Well, affordability usually would combine the total cost of it would compute the total cost of the shirt and then determine if it is affordable or not. So price and shipping cost could be the two features that can contribute to the affordability of this shirt. Um, how can we know of the awareness? Well, marketing alone could contribute to if people are aware of this item being available on the in the market or not. And then perceived quality, like what do people think about this? Two factors can contribute to it. One is the price, and another one is the material. So if it's of a high quality material, people are going to think about it as something valuable. And another thing is price is also contributing to that. So if something is expensive, automatically we think that this is something that would be of high quality. The point that I'm trying to make here is not these raw features always contribute, or not. It's not always directly visible from these raw features to determine if it's a top seller or not. It's usually more better if we come up with these high order or some more advanced features, which can make it much more easier for the model to determine if it is going to be a high order, if it is going to be a top seller or not. So if you think about a logistic unit, it is just simply taking these raw features as input and producing an output. It is not taking care of these intermediate factors. But if you look at the architecture of a neural network, so I told you that this perceptron here, this is just one unit or just one neuron. And what does a neural network consist of? A neural network consists of lots of these. So a typical diagram that you might see of a neural network would be something like this. So you have these inputs, and then you have this one logistic unit here, another logistic unit, another logistic unit, and you can add on these logistic units. And all of these inputs are connected to each of these logistic units separately, so with different set of weights. So W1, W2, W3 up to Wn is for this one, and then for this one, it could be, let's say, K1, K2, K3, and so on. So the point is, these logistic units, or these multiple perceptrons or neurons, they are connected to the input features are connected to them using different set of weights. So what can happen is these different logistic units could then be accounting for different features or high order features that can then contribute to, just like I said, that can make it much easier for it to predict if this is going to be a top seller or not. So if you can compute these intermediate features and then make use of those features instead of the raw features in order to compute the output probability, you can make the job of this, you can make it much easier for the model to determine if it is going to be a top seller or not. Now, the question that comes to mind is, are we always going to be aware of these factors, these high order factors? Like for this hypothetical t-shirt example, I have explicitly written here these intermediate features like affordability, awareness, perceived quality, and so on. But sometimes for lots of the problems, you wouldn't know what factors are going to be very significant in computing the output, if it's going to be a top seller or not. For majority of the cases, you wouldn't even have any knowledge of it. All you have is these input raw features, and then the task is to determine the output, which in this case is the probability if it's going to be a top seller or not. So what a neural network does is it takes care of this burden from us to come up with these factors manually. It automatically computes these factors, and we wouldn't even know if these factors are what those factors that it is looking for, what those contribute to. Like, there could be no real world understanding of it. It would be computing something and then making use of it to determine the output, the goal, or the task that we are going to task it for. Does it make sense?
So when you say logistic unit, what you basically mean by that is like a nonlinear function within the larger neural network?
Exactly. So what I mean by a logistic unit is this simple concept of the perceptron that I have drawn here. So this is just one logistic unit. The reason I'm calling it a logistic unit is because we covered logistic regression, and maybe it would make it easier for you to understand that, but you cannot call it that. You can just simply say it's an algorithm, or it's a linear combination. We multiply them with weights, add them together, add a bias unit, and then apply a nonlinearity on it, and that's how it is computing an output. The distinction between this and a logistic regression is, in logistic unit, we just simply had to do this once. But now we can combine lots of them together And why would we want to do that? Well, just like I told you, um, the raw features may not directly be contributing to what you're looking for. There could be the features could be combining in certain ways, which would make some more valuable features, some high order features. So what do I mean by high order features? You can simply consider, like I've explained it in terms of this one, but you can consider it in the house price prediction that we were doing. Maybe area, maybe let's say area alone wouldn't be significant, or let's say the waterfront alone wouldn't be significant. But if you combine area with the waterfront, maybe that can come. That could be something that would be more reliable in determining the price of the house. So features combining in certain ways could come up with some other features which would be more effective in determining the output. And that's exactly what neural networks excel at, because they are not just simply directly taking these features and the input features and producing an output. They're combining them in multiple ways through these intermediate layers. Now I have drawn here these logistic units. There are four of them, but in a typical neural network, it could be hundreds of them or thousands of them. And then not just only this one layer, there could be multiple layers of them. So you can include more layers here, which would then take those features that it has determined from the input raw features, combine them in some more ways to come up with something even more complex, and so on. So the longer that you keep on adding these layers and these what are called neurons or perceptrons or logistic units, whatever you may want to call them, the the more complex this neural network is becoming, and the more complex it becomes, the more powerful it is to come up with to identify patterns which would be more significant, and it wouldn't even be like we wouldn't even understand what those patterns means, but it would be something that would mean something to this neural network in order to produce some output.
Yeah, that's really helpful. So the general idea is that in week one, we took the linear regression, which is just a linear model, which now is kind of forming the first part of the perceptron. Then in week two, we took the logistic regression, which adds a nonlinear function to that, and that's sort of making the activation function of the perceptron. And then by combining like lots of those together in a network, you get something that can basically um, emulate any kind of nonlinear function. Does that make sense?
Yep. Why I'm not getting any questions from the other guys? It's either you don't understand anything or you understand everything.
Any comments?
Any thoughts? Okay.
Felix, were you about to say something?
The part before was very clear. This part not entirely clear, but I was just waiting to just hear more, and then I'm sure it becomes clear.
Which part is not clear?
So after you, so the previous part about the the kind of implicit factors, and how the neural networks are using data to predict a certain outcome, but we don't really know the actual factors within it. That was very clear that until that point, and then after that it was not as clear.
Yeah, after that we didn't talk much. Maybe after this it's just the rest of the stuff that I'm going to say would be just the implementation details of this thing. How do we implement this, and some technical terms that are given to it, how this network produces an output, which is called a forward pass, and then how do we train it, which is called a backward pass, and all those things. But the essence or the real intuition behind the neural network is just that instead of taking the raw features and directly applying some simple like linear combination, just like we have been doing in the linear logistic regression, they come up with these intermediate layers. And the
Yeah.
bigger you make these intermediate layers and the more these units, perceptrons that you have in them, the more complexity you are introducing into this network, and you are making it much more versatile and diverse to capture any kind of complex phenomena. So suppose if I have an image and I want to assign some label to it, if you would try to accomplish this task using, let's say, a linear a logistic regression, just taking the pixel values and attributing them to a label, this is a highly complex phenomenon. We know what goes on. Like when you look at something, there is lots of things that are happening in order to determine if it is an object, let's say a cat or a dog. Logistic regression, just by looking into the pixels, would not be able to come up with modeling such a complex phenomenon. But if you introduce lots of them, introduce these non-linear functions into them, arrange them into these layers, you have now introduced lots of complexity. In other words, this model is now capable of learning any highly non-linear and complex relations. This is literally the entire idea behind neural networks. And all the rest of it is just simple implementation. How do you make this? How do you compute an output from this thing? And how do you train this thing?
All right, let me ask one question. So
Yep.
so we have certain data and we're trying to predict the output, but we don't really know what features are used, right, to predict the output. So I'm wondering, how can we know that our data is sufficient, or how can we improve maybe on, like, how can we find cues how to improve the features that we are inputting into the model? Right.
Okay.
That's basically my question.
Yeah. So just like here, when I was explaining this example, these features that we have here, these are, you can say, handcrafted features. So usually what happened in the traditional era, when when neural networks were not so bigger and not so complex, what people would usually do, because these raw features were not very helpful, it was not very much like the algorithms were not, SVMs or other traditional algorithms were not able to come up with accurate predictions. Then what people would do is they would come up with these handcrafted features. So you know the concept of affordability. You handcraft this thing yourself, or you know the concept of awareness and perceived quality. So you know how to combine these into these features and then make use of them, because now you know that these are more it's more it's more easier for the model now to make use of this and produce an output. If you people are familiar with, let's say, the sound, the speech signals and its Fourier transform, if I want to, let's say, recognize a speaker, if it's if a male is speaking or if a female is speaking, using the sound samples directly, it would be much harder for the algorithm to determine from it. But if you take the Fourier transform it and come up with, let's say, the frequency domains, we know that female voices have a higher pitch and male voices have lower pitch. Now, by transforming the sound wave into the frequency domain, it is now much easier for any model to determine. It would just have to look at the pitch. If the pitch is higher, it knows that it's a female. If it's lower, it's a male. So we are handcrafting those features in order to make it easier for the model. What neural networks made possible was that you don't have to worry about that. All you need to do is to feed this raw features as an input, and you don't need to worry about what features are going to be important for me. You won't even understand what features it is looking for. And this implicit feature extraction, this ability of neural networks to come up with these intermediate features, which is then highly reliable for the model to determine to make its decision on it, is the real power of neural networks. So the feature extraction is now not your headache. You don't have to worry about it. All you need to do is to construct this network and these implicit layers, these internal layers, would come up with those features which would be reliable for the model. Now, how much data do we need? Your other question was, usually, if you compare it with the traditional models, neural networks are really data hungry, and that's why I said that initially they were not very fruitful because of the limited availability of the data. But as data kept on increasing, the performance really started shining. How much exactly the data is required, that's like you wouldn't know how much exactly the data should we have. It's like subjective to every problem. Sometimes it works on less amount of data, but sometimes you'd have to come up with lots of lots of data in order to make it work. So that varies from problem to problem. Usually if you are doing, let's say, image classification, a data of, let's say, 1,000 or 2,000 pictures would be enough to train an image classifier.
Yeah. So my question was, so let's stick with the example of the voices. So let's say if you handcraft the feature and you say, okay, pitch is important, and then maybe you can derive from that, okay, you need to have a certain resolution of the audio data to optimally like represent that pitch, and then you can predict the outcome better. That is quite transparent. But if you work with neural networks now, you don't know what features, right? So you wouldn't know that maybe you need to have this or that data or higher resolution data. So that's why my question is like, is it just trial and error that you choose different data and you see like what's the accuracy of the output, or is there any way to kind of to steer that outcome?
Okay, so once you come up with like, let's say the problem is to detect if it's a female voice or a male's voice. All you have are the speech signals, a person speaking, right? So if you want to solve this problem using a neural network, it's not like you would have to first try with the speech signals and then go and gather something else for it. The data is now fixed. You have that data. At least you know that this would be enough to determine if it's a male speaking or female speaking. Now, what kind of features are important? Just like you said, neural network is computing that internally, and this is exactly the problem with it, that we don't know what features it is looking for. If you try to look at these intermediate neurons and try to make sense of the numbers, it won't make any sense to you. We'll show in the next week. We will shortly see the CNNs, which are very good at images. So the convolution, the filters, they are computing something. Even if you visualize those things, it would make no sense to you. What is it looking for? But still, it would be able to come up with some correct predictions on it. So the same goes for the problem of the speech one. Like, you wouldn't know what features are important. The neural network, it is the task of it to determine that. How is it determining it? The concept stays the same. You have this model, the weights are randomly initialized, and you train them using the gradient descent algorithm that we were talking about. So that's all that you have a control over it. The rest of it is literally implicit to it, and that's why it is also called sometimes a black box algorithm, for the simple reason that you don't know what's going on internally.
Yeah, I had one comment on Felix's question. I think what you're trying to get at, Felix, is like the whole problem, like subset problem of machine learning and like neural networks, is called interpretability. It's like the ability of a human to understand what the network is doing, and that's like a very open problem that no one actually really understands.
Exactly.
So if you could try to solve that, that'd be really cool. But it's just very difficult.
Yeah. There have been some attempts in order to explain the output of how these models work. So in the previous session, I think Felix, you were there when we explored the SHAPE package or Shapley values. Tools like these people are trying to have an attempt in order to decipher what's going on internally in the model. But just like Redden said, it's an open problem. Researchers are still trying to figure out how it is making decisions. And it's one of the principal criticism on them. And it's usually what is preventing them from getting applied in sensitive areas like medicine or something, because doctors or people are not just interested in how accurate the output is. They would also like to know how it arrived at its decision. And if you don't know how it arrived at its decision, there's no transference in its decision making, and that's why it's not very acceptable in such sensitive fields. So, yep, that's an open problem.
I did have
All
one
right.
other question.
Mm-hmm.
So you were talking before about like how basically adding more neurons or adding more layers to the neural network will basically allow it to handle more complex like relationships and more complex like non-linearity in the data. So then my question is, what would stop us from just like adding arbitrarily large amounts of neurons and just throwing it at any problem and saying, yeah, you can solve it because we have more neurons? Like, what is the constraint there?
What would stop us in adding more layers? Principal issue that would stop you is the overfitting of the model. So if you are looking at a problem, and let's say you want to solve it using a neural network, you throw some layers, it's not working, you keep on increasing number of layers. A point would come when the model would be doing something very it would be performing really good on the training set. It will be kind of memorizing the entire training set, but it will be not generalizing on the test set. It will not producing something reliable on the test set. At that point, you know that keep on increasing the layers is not making it's not helping me. It's just literally memorizing the data, and then you would have to make the model less complex, reduce the number of layers so that it is not overfitting to it. So overfitting is one phenomena that usually stops you from adding. Just simply adding more layers wouldn't be a fruitful solution to it. For other problems, sometimes like usually people start with smaller, shallower networks, but if it is not performing good enough, then you usually try to make the model more complex. Usually that is represented by the underfitting phenomena. If the model is not even doing good on the training set as well as on the test set, then you just make the model more complex. But a point would come when the model would start doing good on the training set, but it would not be doing good on a test set, and that's what is a typical overfitting is. So you then have to prevent the model from getting too much complex. That's kind of an upper bound on how much complexity or how much layers you can add to it. Other concerns could be the computational cost that you have, computational resources that you have. Increasing the model is obviously increasing the computational burden on it. So that's also something that you have to take care of. Another constraint is, of course, the availability of the data. The bigger the model, the larger amount of data it would be needing. So usually there's a general wisdom, although it's not strictly applicable, but it is said that the number of examples that you have in your data should be greater than amounts of parameters that you have in your model. So let's say you have a model with 2,000 parameters, which is a very small amount. Your data should be at least greater than that. But it's something that is not strictly applicable. You can have models which have greater parameters to train them on less amount of data. But it varies from problem to problem. Some problems it works, for other problems it usually doesn't work. So you don't have to just come up with different strategies in order to make it work.
Cool. So basically, it's a constraint. Well, one constraint is the amount of data you have. I'm assuming that like it's harder to overfit data when you have more of it. Like a model.
Exactly.
Yeah. So like that's kind of a similar problem, and then the other problem is computation. So like a larger model takes longer to train, and so you have to have more compute available, and it be willing to like sacrifice more time.
Yeah, and you also have to look at the overfitting phenomena. So if you make the model more complex, it would start doing very good on training set, but it would be not generalizing well to the test set. So you should just stop making the model more complex at that stage.
So one thing I've kind of run into when I'm kind of working with some of these models is when, like, if the model is overfitting on my data set, it sometimes helps, like, if you can get more data, you can to make the data set bigger with the same model, and then it, like, the overfitting kind of stops because, like, it's now harder to, like you're saying, memorize all of the data. So, like, that kind of counters that problem.
That helps. The greater the amount of data you have, it usually prevents the model from overfitting. That's a typical remedy to prevent the model from overfitting. The smaller the amount of data, like I was just working with a transformer model, training it on to produce an expert prediction, I just had a fewer lines of text. The parameters, typical parameters in a transformer model are in millions, even if it's a smaller model. And all it was doing in 10 to 20 epochs, it just memorized the entire text that I had, and all it would be then producing is the exact text that I have. This is a typical case of overfitting, where it just memorizes the entire training set, entire data that you have. If you have a more diverse data, then in that case, the model would be not possible for it to memorize the entire thing, and it would generalize well to produce general text, like produce text that is not in the training set. There are other techniques that can also prevent the model from overfitting. So you can also, like, this is usually applied in imagery data, in CNNs. You can augment the data, just simply randomize the data, flip the images, apply some noise to it, and that's how you can increase the amount of data. Another thing that you can do is take a pre-trained model and then fine-tune it, in which case, even if you have a smaller amount of data, it would still work better because some of the filters are already tuned, they are already trained. You just have to fine-tune it to your own data. So there are multiple ways you can get around the problem of overfitting or the problem of limited amount of data. All of these things that we've been talking about comes when these are the problems you'll be facing when you want to take a neural network and apply it to some practical problem in order to solve it. But just to complete the
This is making me excited. This is making me excited to do some coding.
Yeah, but just let me quickly talk about these terms. I know I have like horribly introduced the entire thing, which you people might feel lost. You can ask me questions as much as you can. But what a forward pass just simply means in a neural network is that if you have the weights are already trained, producing an output from a neural network is what is usually called a forward pass. So how does a neural network makes its predictions? For simplicity, we are just simply taking this neural network where we just have these one hidden layer. So usually the layers that come in between input and output, these are called hidden layers. So we just have this one hidden layer, and we have just two neurons in this hidden layer, A1 and A2. How is this neural network going to produce an output? So I'm saying we have already figured out the weights, W1, W2, W3, and Y1, Y2, Y3. So A1 is generated by simply taking the linear combination of X1, X2, X3 by multiplying them with W1, W2, W3, adding them together, adding a bias unit, applied nonlinearity on it, and that's how it is producing an output. Same goes for A2. You just simply multiply with the weights, add them together, add a bias unit, apply nonlinearity, and then the way output is produced, you now have these two hidden units connected to the output using these different weights, C1 and C2. So you multiply A1 with C1, A2 with C2, add them together, and then apply this C, which is the bias unit for this neuron here, and apply nonlinearity on it, and that's how an output is generated. So producing an output from a neural network is what is given the term forward pass. So that forward pass. Now, there's one other question that remains, that is, how do we train a neural network? Now, James wants to do some coding. Maybe if you want me to skip that, we can skip that, or if you want me to talk about the backprop, we can go into the backprop, but it will take the remaining 15 minutes.
Yeah, what would you all like to do?
Maybe let's do some coding first. I really want to find out what's the backprop. I think I heard about the general working of it, so maybe coding.
All right, we can also send a recording of the backpropagation explanation as well.
Yeah,
we can do that as well.
Okay, great, works for me.
Thanks.
I'm happy with that. So yeah, so what we're going to do now is I'm going to show you how to implement a neural network in Python. And I know Braden has done this before, right? Has anyone else done this? Right?
Nope.
So there's a couple of different libraries that you can actually use for this. Hey, Braden, are you with us? Okay,
Yeah, I'm here.
cool.
I'm just cooking breakfast.
You've implemented. Nice. What's for breakfast?
Eggs and toast.
Wonderful. And what libraries did you use before when you were making a neural network?
Mostly PyTorch.
Cool. Does anyone else know any other libraries you can use to train a neural network? So there's a few, and today we're going to use TensorFlow with Keras. So to open this this little project, just go to the course page here under neural networks, and click on the neural network mini project. And so we can apply a neural network to any kind of problem. So in the first week we did regression problems, and in the second week we did classification problems. So I wanted to give you an example of both, and so we have both examples here. Today we'll probably just go through the regression problem. That's the same as the given a house with all of these different features. What's the expected price of that house? We could also apply a neural network to given a tissue sample. Does this look healthy or does this look cancerous? We could also create a neural network that does that, and they're similar except for the one layer at the end. But yeah, we're just going to do this this regression today. And for your project, what you'll do is you can take anything that you've done already, whether it's the regression from the first week or the classification from the second week, and apply a neural network to the exact same problem, and see if hopefully your loss should be less and your model should be more accurate by using a neural network, as it's able to discover the hidden features inside of the data. So this is our example notebook. By the way, does that make sense, everything I said so far? Okay.
Yeah.
Yes.
So this is a notebook that we've put together, which shows simply how to apply a neural network. Hey, Brayden, I think, is that noise coming from you, Brayden? I think I might go on mute.
My bad.
Smells good though. So this notebook is showing us how to apply a neural network to the housing price prediction regression problem. And as you look here at the top, we're using NumPy and Pandas as usual. We have charts, and then we have here a lot of the traditional machine learning stuff, sklearn, that we did before, which we still need to scale the data, to make the train test split, and to calculate the loss. But then we also have something new here, which is TensorFlow.keras. And Keras is a library that I guess has sort of been eaten by the larger TensorFlow library, which contains a whole bunch of useful stuff for deep learning. But yeah, this Keras sequential model is the larger model that lets you create a neural network, and then the dense layer lets you create one layer in your neural network. So here I've downloaded the exact same data set that we used before and read the data set exactly as we did during the first week of this course. And likewise, I've selected I've selected all of the features like we did in the multivariate regression problem, and I've selected the feature that we want to predict. I've scaled the data, so this just subtracts the mean from each of the input features and then scales it over the range of the lowest to the highest in that, so that everything is on an equal scale when we're training the model. Created the train test split so we can test it later. So this right here just refers to the fact that there's 21,000 input rows in the data with 18 features. So all of that should be, should be super familiar for you all, right? Cool.
Mhm.
And this next part should not be familiar for you if you haven't used Keras before to create a model, to create a neural network. And this is the code where we define the architecture of the neural network. Now, it's also very this here in the code is pretty much reflected exactly here in this model 2.summary, which is sort of a nice table to look at it. But what you see here is the same thing, is that we have 3 layers in this model. And can anyone sort of try and read this code and tell me what they what they see is happening here in each of these 3 Python statements?
Question: is a dense layer the same as a fully connected layer?
Is a
that
dense
the
layer
same thing?
Is a dense layer the same as a fully connected layer? Yeah, right?
Yep.
Yeah.
Yeah, I think in PyTorch they're referred to as fully connected. It just means that it's like
Yeah.
a matrix multiplication, so like every row in the input is connected to every row of the output, or in each neuron in the output, something like that.
That's correct.
Okay.
Exactly. So, so what we see here is, yeah. Sorry. Okay.
Anybody else want to give it a shot? Or I can go.
Yeah, go ahead, Brayden. Brayden. It's actually super easy because I've also written here.
Did anyone or I can go?
Yeah, Brayden, you can go.
So it looks like we have the first layer is. Can you hear me?
Yeah, we can hear you.
Can you hear me?
Yeah, Brayden, we can hear you.
Yeah, so there's kind of like 3 layers. The first one looks like it does like basically the inputs to map to a hidden layer with the ReLU nonlinearity, and then it goes to the second layer, which does basically the same thing, but it looks like it kind of expands it, and then at the end it just maps to a single output. Is what it looks like. I don't know.
Yeah. So exactly. So this function.
I don't know. Okay, I'm just gonna stop talking.
This dense function. Yeah, there was a little bit of crossover, but it's fine. This dense function takes the number of neurons that you want to have in your layer, and then the activation function, which then combines, which then decides on the function that's used for the output of that layer, the output of each neuron in that layer, which is passed on to the next layer. And so, in this first layer, we have 10 neurons. The second, we have 20. These can be anything that you want. The last one, it has to have 1 neuron because otherwise you'd have multiple outputs, and the model really just has 1 output, which is the price. Now, Brayden was mentioning that each layer here is really a matrix multiplication. Of course, then you have to add the weight as well, which he didn't mention, but it's also important. And then there's the activation function. So those 3 steps, the same that Naveed mentioned, are the same that are happening here. If we would look at how this is implemented in something like TensorFlow, you'll see there's a lot more code going on here. But in TensorFlow, and the reason why is that you have to, here you have to explicitly define, okay, there's a matrix multiplication, then we're adding the biases, And that's and the same in PyTorch, although it's a little bit simpler. It's defining each. It's actually calculating each layer one at a time in this x equals format. So it's doing it sequentially. But I just wanted to show you that the different libraries, they use different amounts of code to do the same thing. And here we're just doing it in Keras, and it's this super simple, easy way to.
James, just a quick comment on the activation function. So here you see we are using the ReLU non-activation. So when I was introducing, we talked about the sigmoid nonlinear activation. So the sigmoid is just squashing the output between 0 and 1. What ReLU does is it blocks the negative entries. So if the value of the z, which is the linear combination, is below 0, it's negative number. It just simply prevents it from flowing through the network. So it's making any negative number equal to 0. And if it's something is positive, it's just producing it as a linear output. So if it is 10, the output is 10. Now, the question is why we are using ReLU activation function. The simple answer is sigmoid usually flats out at 1 and 0, 1. Yeah, here you can see that. So the result of this is, remember, the rest of phenomena stays the same. This model is producing something, and then we have the true output. We are computing the difference between the two, which is the cost function. The goal is to reduce the value for this cost function, for which we use gradient descent, for which we use derivatives. And if the activation is sigmoid, and you take the derivative of a sigmoid activation function, since it is flats out at 0 and 1, the gradients are going to be very small. And if the gradients are very small, the updates that you are introducing to individual weights would be very small. In other words, the model would be just simply taking much longer to train. It wouldn't even train in some cases. So that's why a sigmoid is painfully slow. And it also is shown that it doesn't work for lots of the problems. While on the other hand, ReLU activation function, it's faster to train because gradients are not 0, and it's numerically also stable. And it also works for majority of the problems. So for 95% of the cases, you will be making use of a ReLU non-activation function. There are other choices of activation functions as well. So you can try tangent hyperbolic, CeLU, leaky ReLU, and lots of different variations. Everyone has its own pros and cons. Each of them are introduced in different research papers for specific problems. And they have provided details of why it is working, why it's not working. It's not something very solid. So you can also always experiment with them to see which works.
Cool. Thanks for that. So yeah, the last thing I just want to show about the model architecture here is, could someone explain to me why these layers have the number of parameters that they do? Here we've defined the number of neurons in each layer, right? But where does this parameter come from? How does it get from 10 neurons to, in this layer, to 190 parameters? Does anyone know? So a hint would be that the parameters is the number of the weights and the biases in that layer.
So usually in a network, there's like the nodes, right? And then there's the connection between the nodes.
Yeah.
And so all these connections are, I think, produce like the weights, right?
Yeah.
If I'm correct.
Exactly.
And then those would be the parameters. But I'm not exactly sure why exactly 190.
Exactly.
Here.
No, but I think you've really hit it spot on. So the number, there's a number of neurons in each layer, and between each layer, there's connections between the past layer and the next layer, right? And those connections each have a weight, right? So what's the number of connections between this first layer and the past layer, which is really just the input?
So it should depend on how many features do we have.
Yeah, and we should have 18 features. So the input has 18, and then this layer has 10 neurons. You can sort of think of that as being like the 0th layer. You know, it has 18 values in it. This one has 10. So if you
10.
multiply 18 by 10 neurons, you get 180 connections. And then we have to add 10 so that each neuron has a weight.
Okay.
Twice.
And if we look at the connections between this layer and this layer, we get 10 times 20 connections, so 10 times 20 weights. And then we have to add the biases. That's what I meant to say before. So that would be 10 more for each neuron gets a bias. Make sense?
20 more. Yep.
Yeah.
Yeah, it's 20 more. Still waking up. So the next phase is you'll recognize this syntax easily, is to train it. And I won't train it now because it will take a few minutes. You'll find that the more parameters you have, the more time it takes to train. But one note here is that we actually pass in the validation data to this. It obviously is not using the validation data to train the model because that's the whole point of validation data, but it does use it to give us this handy metric as we're training it. What's the loss on the training data, and then what's the loss on the validation data? So if we put that into a chart as we're training our model, this is what we see. Felix or Nissan, can you describe to me what this chart shows?
Can you move the video?
Sorry. Yeah, sorry. Let me push that over to the side. Yeah.
Okay, so I guess the loss is reduced over time. Like the more you train, the lower the loss. However, it's kind of leveling off, so it's kind of asymptotic curve.
Yeah.
So it doesn't go to 100%, or it doesn't go to zero. The loss doesn't go to zero.
Exactly. And each epoch.
That's because the y-axis, if you see, it's in the order of 10 to the power of 11. So it seems like it's flattened, but if you zoom on after, let's say, the 50 epoch, you'll see that there's still some decrease, but it's not much as compared to the initial one. That's why you see it's getting flattened out.
Exactly. So each epoch means we're running back propagation with all of the data, and each time that we do that, the model becomes more accurate. Now, up to a certain point. Now, Felix, one thing I think you didn't mention was that there's two different lines here, right?
Yeah, so I don't know what it is exactly, but I guess as it's annotated here, there's like one line is for the training set, and then the other one's for the test set, and we see that they're very similar, but they're not completely identical. I guess it's because there's different data in these two sets, and so those the loss kind of varies a little bit, but not by that much.
So the test data set is houses that we put aside that the model cannot see during the training phase. And so we would expect that since it's never seen those examples before, but it has seen the examples in the training data set, that those should be at least a little bit harder for it to predict, which is why the loss for the testing data set is higher.
Is that also kind of the score then to to show how much the model can generalize, basically?
Exactly.
Yep.
And
so the test loss is always going to be slightly higher than the training loss because it's the data has not seen it before. Slight difference is okay, but if there's bigger difference, then it means that the model is performed really good on a training set, but it's not generalizing to the test set.
In the beginning of training, you may see some weird fluctuations. Like actually here we see that in the beginning it does better on the testing than on the training, but that comes out in the wash once it actually starts training.
Cool.
And that's the whole example. So here we just run through the RMSE and the mean absolute error. And if I want to, I can look up I can go back to our first assignment, and I can look at the same variables, the same values for the linear regression that we did. So I'm just opening that up. So here on the linear regression, we saw, oh, this is the single variable. I should probably go to the multi-variable, which is more fair comparison. So here we saw the root mean square error was 198,000, and here it's improved a bit, but it's definitely improved, which is the idea. And when you go and you do this on your own data sets, which you should do before Monday, we're looking forward to hearing, how much it improved for you and why. Of course, that would also probably improve if I would use a model that was maybe a bit bigger with some more parameters as well. So we've used one of the most simple models, simple architectures possible. And you can go ahead and you can try that out on your own data.
So just a quick comment, what can you experiment with? You can increase the number of layers. So here we have just 2 layers, one with 10 neurons, meaning those 10 logistic units that we were talking about. Another one is having 20. You can increase the layers, and you can also increase the number of neurons in each layer. So that would be one thing that you can try. And then you can also try different loss functions. So you have MSE here, mean squared error, as the loss function. You can try MAE as well, which is also built into the Keras. So you just have to replace that MSE with MAE and try to figure out how has it changed the prediction of the model. So that's also something you can change. There's not much that you can do for the rest. You can play with the bit size and all those details, but that would be something which would make more sense when you work a lot with neural networks. For beginner, usually the beginning lesson, usually number of layers and neurons would be a typical place to experiment with.
Great. Yeah. Everyone think they can do that?
Sure.
Perfect. Love it. So yeah, we've already gone over a little bit for today. So yeah, we'll just end it there. And I'm going to send you the link to where Naveed has wonderfully explained backpropagation, so you can have a look at that.
Thanks.
Okay. See you guys then.
Thanks, everyone. Thanks, Naveed.